grand unified theories, and they made all kinds of, it turned out that they had implications for things that happened in the early universe. And I'll talk about a few of them, dark matter particles and inflation, but just, it was a wild old time, and I found some pictures. So we like to call this the go-go junk bond days of early universe cosmology, where every day, and Hank can testify to this, we'd come up with a new idea about how the universe could have begun and how it would be today. And this is the book that was mentioned by Mark. And this is myself at the, look at those Birkenstock shoes, aren't those? And Rocky Cobb. And I thought Hank was going to, maybe he did mention this, is that one of the things that we're most well known for is pioneering the sales of t-shirts at physics conferences. Before that, no one sold t-shirts at physics conferences. And this one says, Cosmology takes guts, where guts meant grand unified theory. So this connection between, and these were the Wild West days. No one knew where it was going. We just knew we were having a really good time, and that's what Hank was trying to say earlier. I think that was the English for it. So, three really important ideas that have driven cosmology since, which I want to talk about. Inflation. And this is a brief period of very rapid expansion early on. I'll give you more of the details, which explains the smoothness, predicts that the universe should be uncurved, explains the heat of the Big Bang, and predicts where the seeds came from. Dark matter. So everybody's heard of dark matter, right? I'm going to tell you more about it, but you've heard about it. So one of the big mysteries in cosmology is, what is the dark matter? And so another prediction is dark matter is not dark stars. It's not black holes, it's not neutron stars. It's a new form of matter. That's pretty wild. And then the last one is it gave us dark energy, which we'll talk about in turn. So let me first talk about inflation. And to catch your interest, I refer to this idea, even though it's due to other people, as the most important idea in cosmology since the Big Bang. So Alan Guth and Andre Linde. This is a really important idea. And it's asking the following question, and which this is coming back to what science is all about. It's asking the right questions. And that is, you know, we have this highly regular universe today. You took the tour of the universe last time. I hope everybody came back. And it's very smooth. And so the universe had a beginning. That's kind of the big thing from Hubble. You know, that's before Hubble, we didn't know the universe had a beginning. Is that the way the universe had to turn out? Were there other ways to begin the universe? And what Stephen Hawking and his student Collins did was they showed that if you threw a dart at the dartboard, which represented all the different ways the universe could begin, everybody with me on that metaphor? That, and I'm going to use a couple of technical terms here, in a jiffy, the jiffy is 10 to the minus 43 seconds, the universe would be a mess. So that, put it another way, that our universe began in a very, very special way. So it's not that we couldn't have evolved a universe like ours, but to get a universe like ours, you would, the bullseye is absolutely tiny. And so the question was, so that got at people thinking, is there a way that we can make that more automatic? Is there a way that we can start a universe in a more arbitrary way so that it's guaranteed to look like that? So this is a wonderful thing about science. I'm sorry to keep using the word wonderful in science in a sentence. I was told I can do that as much as I want as long as I don't mention the name that begins with J and ends with N. Because I'm getting a bonus if I don't say his name in these 3 lectures. Don't you say it. Okay. So is this a good question or not? I mean, It turns out it's a really good question. And so let me tell you about inflation. So inflation, the key thing, the headline here, short period of very rapid expansion, and you don't have to read this part, but it's driven by false vacuum energy. So it's a particle physics energy that I won't talk much about, but so this comes from these ideas in particle physics. And, well, what do you mean short period of rapid expansion? In a jiffy, the universe grows in size by more than it has since then. That's a lot. So it gets really big. And so here's the idea. Here's how it works. So it's this big growth. So let me show you how it works. So here's this mess. Here's the messy universe. And we focus on a tiny little bit of it that might have been, that we could imagine to be smooth. So the mathematicians tell us that if we look at the most crinkled piece of paper and look at a tiny little bit of it, it's smooth. So you can all try that experiment at home. And so you take that tiny little bit that is way too small for us to be in. But now you do this inflation, so this very rapid, today we would call it accelerated expansion. You blow that up, and this little black circle becomes this big black circle, and it remains smooth. And if it had any curvature at all, it's now so big that it looks uncurved. Just like, you know, if you have a small balloon, it looks really curved, and if you blow it up, the curvature becomes less and less. So it's smooth and flat, and the idea is this is where we live. So we live within this. So this burst of inflation creates a happy home for us, a big smooth patch, but there's more. And the more is that this vacuum energy, let's go back to the last picture, this vacuum energy decays and turns into heat. It becomes the heat of the Big Bang. So it creates the heat of the Big Bang. Now, this is sort of the piece de resistance, how we create. So now we've made a smooth universe, but we don't want an absolutely smooth universe because we need the lumps. How do we do that? Well, what we know is in the subatomic world, things aren't smooth. Things are jumping around. Things are fluctuating. That's quantum mechanics, the uncertainty principle, however you think of it. If you look at the quantum world, things bounce around. So we have lumpiness, but it's lumpiness on tiny, tiny scales, angstroms, nanometers, everybody knows nanometers. And galaxies, this is part of the quiz, how big are galaxies? Millions of light years. So how do we turn that lumpiness into, how do we take advantage of this? Well, how do we get it to millions of light years? Well, that's the enormous stretching. So remember, the expansion of the universe stretches everything. So it stretches this so that those variations become those variations. And then we put secret sauce. There's theory secret sauce, because these are fluctuations in what? I'm not going to tell you. But they eventually should be fluctuations in the matter. And so this was the most fun I ever had as a scientist. This is a paper I wrote with Jim Bardeen and Paul Steinhardt, where we figured out how to do this. Turned out some other people figured out how to do it, but it was still very exciting. So you're able to take lumpiness, quantum fluctuations on small scales, and turn them into the seeds for galaxies. And so if this is correct, this is amazing. This means that when you look at the microwave background, what you're really looking at is the world's largest IMAX, or the universe's largest IMAX. It's the subatomic world projected on the sky. Across here, you're seeing quantum fluctuations, and they started, this length scale, when they started, was thousands of times smaller than a proton. And they created the biggest things in the universe. So would anyone want to challenge that this is a deep connection between the very big and the very small? Okay, so that's a very big idea. We'll get back later to whether it's a correct idea. Why did I want to say this? Well, we love to use scalar fields. What's a scalar field? How many people heard about the Higgs discovery? that Higgs is a scalar field. The Higgs is not what does this. But the fact that Brad and his friends showed us there's at least one scalar field, we hope one of its cousins did it. Okay. It explains the smoothness, the heat. It predicts that we are the uncurved universe, the flat universe. We call it the flat universe. That's jargon. It predicts the nature of the lumpiness. We'll come back to that. And for next time, just put a little footnote in your brain. It also produces gravity waves. It puts ripples in space-time that we'll come back to. Okay. That was inflation. Let's come to dark matter. Dark matter is a really fun subject because the story is terrific. It begins with this guy, Fritz Zwicky. Today, he would get sent home from school with one of those little notes, doesn't play well with others. Very, very smart guy, very, very cantankerous. This is a picture of him describing what a spherical bastard is. A spherical bastard, well, it's kind of like your dean. Oops, there's a dean here, I think. It's a person, no matter what direction you approach them, they're a bastard. But he was an extraordinarily, he was way ahead of his time, and he discovered dark matter. I think the correct date is 1933, but it doesn't really matter. He was way ahead of his time. And let me just describe the dark matter and then work into this idea that it's a new form of matter, which is really a radical idea. So I think, there we go. That's a much more proper picture of him sitting at the telescope. And I think I showed you this last time. This is the Coma cluster. A wonderful cluster. Zwicky was one of the first to study clusters. And you know what I didn't show you last time is this, which it's really fun how discoveries are made. So what this is, I showed you the Hubble Deep Field. This is, which is a tiny patch of the sky. This is a really big patch of the sky, and I just want to show you how, even someone as dumb as me could have discovered clusters. So this is a big chunk of the sky, 40 or 50 degrees across in each direction. Each dot is a galaxy. And so first of all, what you see is the galaxies. If you just looked around here, it looks like they're randomly distributed. Jackson Pollock was painting the galaxies on the ceiling or something with dripping paint. And then you see, oh my God, look at that. What's going on there? And what's going on there? This is Virgo. This is the one we've been invited to join. And I told you actually Virgo was pretty small, but it's really close, so it's big. And this is Coma. And Coma is really big, but it looks small because it's far away. And so astronomers have meticulously, stared at the photographic plates and looked for where, that's probably a cluster, where there's a higher concentration of galaxies. So Zwicky studied Abell 1656. There it is again. And what he did was to measure how fast the galaxies were moving. So, this is not all the galaxies. And what he found is that the galaxies have random motions, thousands of kilometers per second. And so the question naturally arises, how come the cluster doesn't disperse? You've got this galaxy going that way, that one's going that way. Why don't they just disappear? And of course, what is the answer? The answer is gravity. And so now there's a little math problem. Is there enough gravity? If you look at the gravity of all the stars and all the galaxies, is it enough so that as this, let's pick an easy galaxy, as this galaxy goes roaming out, that the relentless tug of the gravity of all the stars and all the other galaxies pulls it back? Everybody got the idea?